Hey, Miguel, feel free to ask any questions if you have them. You can also go ahead and type in your first and last name on the chat so I have your row. Hey, Giovanni and Joseph, feel free to go ahead and chat your first and last name so we'll have you on roll in case you get bumped out accidentally or whatever. And we still have 3 minutes, so you also can ask me questions if you have any. Still got about a minute left, plenty of time. All right. Well, we got five of you in here anyways. It's not too bad. Uh, I'm sure a couple other people will show up in a few. It is 5:20 now, so we should go ahead and get started. I want to let you know we have finished chapter 4. You can look for more examples in the textbook. You can look for more examples on my YouTube channel. You can ask me examples. You might even look, for instance, in my last night's class for 242. So that'd be the date would be 10012024. So if you do a search for that, uh, in my YouTube channel, you should be able to find my PHY 242 class from last night. And that particular class at the end, I had one of my students uh, come to the meeting and ask questions on stuff related to 241. So at the very end of that, you can find some help on vectors and some other problems. So if you need any stuff like that, just definitely check it out. I'm also making more videos. I had to miss classes today, face-to-face classes at school. So this lecture is sort of helping for that 241 class that would have met today. So anyways, we're going to go ahead and get started. Please take time to go ahead and chat your first and last name. So we'll have it in the roll. It looks like most of you have already done that. Maybe one person hasn't, but anyways, as long as you got that, we'll have you down for roll. And I'm going to start off with a couple of different things. So I want to get you started so you can go ahead and start solving physics problems from chapter 5. And chapter 5 is just a continuance of Newton's laws of motion. So chapter 4 covered Newton's three laws of motion, which is an object in motion tends to stay in that state of motion unless acted upon by a net external. That's Newton's first law, which is also sort of a paraphrasing of Galileo's law of inertia. But you can also paraphrase it again because Galileo nor Newton had knowledge of vectors or anything. In fact, vectors and that sort of stuff was sort of made up in the 1800s, early 1800s. And now, with the advent of vectors, we can use the term velocity, which is a vector quantity, and we can say an object will maintain a constant velocity unless acted upon by a net external force. That's Newton's first law of motion. Newton's second law of motion says the sum of all the external forces acting on a body of mass m is equal to m times the object's acceleration. And that too is a vector equation, but again, Newton didn't have vectors, so all he would have told you is that the net force points in the same direction as the acceleration. So if you add up all the sum of all the external forces acting on the body of mass m, you'll get a force that points in a very specific direction. That direction is the same direction as the acceleration. You could then solve that equation for acceleration, and acceleration would be the net force divided by m. So that's Newton's second law. And then Newton's third law, the easiest way, but the sort of least helpful way is for every action, there's an equal but opposite reaction. What I like to say is the force on object 1 as a result of object 2 is equal to the negative of the force on object 2 as a result of object 1. It's more helpful if you understand how to write that. So when I say the force on object 1 as a result of object 2, I call that F with a subscript 1 followed by 2. And what I'm saying is the vector F with a 1 followed by 2 subscript is equal to the negative of a vector F with a 2 followed by 1 subscript. Okay, so that's Newton's third law. And in the last class, we, of course, made use of that. So now we're going to apply that again. One of the first things we did before was I showed you that weight was given by m times g. I showed you a couple tricks how to solve, for instance, the Atwood machine, which is normally you take two equations. One of them has a variable, in that case, t, that's positive on the left-hand side and it's positive on the left-hand side of the other equation. So the natural solution or the natural way to solve it was actually to add the two left sides and set that equal to the two right sides of those equations. To the two right sides of those equations, and that allowed us to solve for acceleration. Then we could plug the acceleration back in and find the tension in the ropes. We also did a fuzzy dice problem where you basically have a plumb bob hanging from a rearview mirror in a car, and the car is accelerating uniformly. In other words, a constant acceleration. And because of that, the plumb bob that would normally be hanging vertically hangs at an angle theta. And we were able to show that that angle theta is the inverse tangent of A over G. Okay, and we were even able to calculate the tension in that. That one required a trick where we divided one equation by another, which is something you usually don't learn in your math classes as well, even though in principle you could. So now that we have that, we're going into this chapter and we're going to have to introduce a couple things. So for instance, it requires a certain minimum force for an object to go in a circle. Even if you like go out into a parking lot and lock your cruise control on, let's say, I'm picturing a very safe situation here, so don't try this unless it's 100% safe. But I'm imagining like a huge parking lot, like a mall parking lot or an airport parking lot or something like that, that's huge and doesn't have any, poles and sticking up and all this stuff. But if you imagine setting your cruise control at the lowest speed it'll possibly do, which I think is around 30, uh, and then turn your steering wheel, let's say, as far as you can where you feel safe to go in a circle. What you'll do is you'll go in a circle, and if your cruise control is perfect, it'll move at a constant 30 miles per hour. But as we know, velocity is a vector quantity, and a time rate of change of a velocity is, in fact, an acceleration. So the fact that the direction of the 30 miles per hour is changing, even if it stays a constant 30 miles per hour, is an indicator that there's an acceleration. And we need to know what that acceleration is, because what you have to do in order to make something go in a circle is you got to make sure it has that specific centripetal. Notice how I said that slowly. Centripetal. Centripetal, not centrifugal. In fact, there's no such thing as a centrifugal force, Fugal. That's not a real force. It's a imaginary force. That being said, it's okay. It still sort of has somewhat related value. Specifically, people feel like they're thrown towards the outside edge of the car door. If, for instance, you're in the passenger side and someone takes a hard left turn, then you would feel like you're slammed against the passenger side door. And if you actually calculated that apparent acceleration, what you'd find is it is basically equivalent to v squared over r, but it's not really that you're accelerating. It's more that you tended to go exactly straight while the car tended to turn to the left under you. So that's what I mean by it's not a real force. But we're going to learn how to deal with that. And we're also going to learn about friction. So we also learned about normal forces last time, and we didn't do much with it. In fact, I only solved for it a couple times. But the main thing is because we need normal force to describe our description of friction. So we're going to cover those. So since I would like you to start to be able to do all the problems immediately, I'm going to start off with a really quick introduction to friction. So what I want you to imagine, and ideally this is something you can do at home as well. The ideal scenario is I'm talking to you right now and you have like a scientific calculator or something with nice little, somewhat tacky or sticky sort of rubber pegs for feet, if you will. The reason why I would like that is I'd like you to be able to lay it on a smooth surface, such as a bar top or a tabletop or something like that. And then I want you to try to give it a push. And what you'll notice is you can push a little bit and nothing happens. And you can push a little bit harder and nothing still happens. And you can keep doing that. And if you do it very carefully, making sure not to push up or down, but to push purely horizontally, you'll see that eventually you'll get to a large enough force where the actual calculator will begin to move. So that sort of shows there's some minimum force that you have to apply in order to make the object go from sitting perfectly still to moving. Okay. That critical force is actually the maximum static friction force you can get. And static is the word we use to represent the fact that the calculator and the table on which it sets are not moving with respect to each other. So when it's sitting perfectly still, the reason you push on it and it doesn't move is because you've pushed with a force that was smaller than the maximum static friction force. And if you push a little harder and it still doesn't move, then that too is smaller than the largest static friction force. And in fact, we introduced the static friction force as being less than or equal to some quantity. So that's all specifically because of the idea of how I gave it a push and nothing happened. I gave it a little harder push, nothing happened, a little harder, a little harder, a little harder, a little harder, until finally I got to some breaking point at which it did move. And then here's the neat part. And immediately upon it moving, you will feel that it's a lot lower force necessary to keep it sliding along, say at a constant speed, than you needed to get it started. So it evidently took a force up here to get it started moving, but as soon as it started moving, you could lower the force intensity quite a bit so that it move easier. And in fact, that is a fact. What we know is the static coefficient of friction is in fact larger than the kinetic coefficient of friction. So kinetic friction is the friction force you have when the two objects are moving with respect to each other. So for instance, when a calculator is moving with respect to the tabletop on which it sits, then you have a kinetic friction situation. When they're not moving, you have a static friction situation. It turns out that those forces are best described by saying that the force is directly proportional to the normal force. So the friction force in both cases is going to be directly proportional to. Now that I have that out of the way, let me go ahead and share my iPad screen and give you some equations relating this. And I'm not necessarily planning on being able to work any examples for that tonight. Depends on how much time I have. The main things I want to get you through is a way of making sense of this centripetal force we're talking about. I did notice some more people logged in. We actually got like 9 people now. So everybody, please go ahead and chat me your first and last name. So we'll have you for the role. And I'm going to go ahead and share my screen via my iPad. So here comes. And another person came in. It's Diego. Hello, Diego. All right. So we're now looking at my iPad, and I first told you about static friction. So I'm going to introduce you to that. Static friction is given by, I usually write a fancy sort of script F like that, like the F that you normally see for functions. And I just put a subscript S on it to mean static. And the way we introduce this is we say it's directly proportional to the normal force, which is what I call F sub n. And the constant of proportionality, in some sense, is what we call the coefficient of static friction, which is mu with a subscript S. So there's your Greek letter mu. But we want to capture the fact that when you pushed on the calculator with a small force, it didn't move. If you pushed on with a little larger force, it still didn't. A little larger, it still didn't. And then there was some break point at which it really finally moved. So the way we do that is we say the static friction is less than or equal to mu static times the normal force. Okay. So that's the equation we're going to be using. If you look in chapter 5, and this is chapter 5 of Giancolli's book, of course, Giancolli's Physics for Scientists and Engineers, 5th edition. See chapter 5, you'll see there's a table of coefficients of friction. And the biggest thing you should notice from that table is one, the table's there. So when they ask you specific homework problems about, rubber on wood or wood on concrete or wood on wood or something like that, then you can look in that table and find out what the static coefficient of friction is and what the kinetic coefficient of friction is for the surfaces that are interacting. However, the other thing I want you to notice from that table is that the static friction coefficient is always larger than the kinetic friction coefficient. And in fact, that is exactly the reason, and I'll try to explain that to you as well. That's exactly the reason why when we have a winter storm, the weatherman comes on and tells you, remember to turn into the skid. What you're trying to do when you turn into the skid is you're trying to get your tires realigned to the actual direction you're going with respect to the road, as opposed to the direction you were going before you started to skid. In doing so, that allows you to reclaim static friction. Whereas when you're sliding, in other words, when your tires are going in a direction in which they do not slide, in which they do not turn, but slide, then you're actually implementing nothing but kinetic friction. So if your tire is able to spin this way, forward and backwards, but it's moving left and right, that's got to be a kinetic friction situation. So I'll get to explaining that later. So that's your static coefficient, or excuse me, your static friction force equation. And notice it's less than or equal to mu s times the normal force. So if you're ever looking for a problem or trying to solve a problem where they're asking you, what's the minimum force you can apply to make this move, then what they're saying is assume the force is the largest it can be for static friction. In other words, in that case, you're going to take static friction and set it equal to mu static times the normal force. Okay. Uh, Again, though, once it starts moving, it then slips into kinetic friction. And here's the idea for kinetic friction. Kinetic friction is also directly related to the normal force. And in fact, we again use the script F. Sometimes I put the S or the K on the force on the F. I don't always do that, by the way. I did here, but I don't always do that. But in this case, with kinetic friction, it's just equal to mu kinetic times the normal force. So you're just supposed to look up the kinetic coefficient of friction for that and multiply it times the normal force. And once you have that, you then have the friction force. Okay. So remember, as soon as it starts moving, the force of friction switches from static friction to kinetic friction, and kinetic friction is quite a bit smaller. So the force required to just break it loose is actually going to be way bigger than the force it's subjected to once it's broken loose. So it can still actually accelerate. For instance, if you maintain that same force that you broke it loose with, i.e. the mu s times the normal force, if you continue to apply that force, then you're definitely going to continue at an accelerated rate because you now have a force that's larger than the restrictive force of kinetic friction. Okay. So that's it.
Professor, were you sharing your iPad? I think it
I
switched
am
over.
not, you're not seeing it anymore?
Mm-mm.
Oh, that's weird. How about anybody else? Because I've had some weird anomalies with students
It's
sometimes.
showing on my screen still.
It is
Do you
still on
see it?
your screen. I wonder what's
Yes,
going on.
Okay, maybe I'll just try and leave and then come back in. Maybe.
Also, let me know if you down at the bottom or the top where it says you are screen sharing, stop share, that kind of stuff, where that stuff is. You might look
Oh
that.
no,
You don't see that.
yeah, there's two options at the top. It says meeting and then it says your device. And I was just clicked on the meeting. Sorry about that.
Okay. Gotcha. No problem. Yeah, you can go ahead and log out. This is
Yeah,
gonna be on
yeah.
video.
If I click on the meeting.
No problem. Sorry about that, bud. All right, so he's going to be gone, I think, for a split second or two. You are trying to log out and log back in, right?
No, so there's two tabs for me on my Zoom. I just realized the meeting
Something like
tab where I see you, and then there's a tab for your device,
Oh,
and that's
cool.
your iPad.
Okay. That's good to
Yeah,
know. So I
I
was
got it. Thanks.
myself. So thanks. Appreciate that. All right,
Yeah.
so we'll go ahead. What I'm going to do is I'm going to introduce you to a vector function. So I introduced you to this a little bit when we first started talking about chapter 3, projectile motion. I said you can actually indicate the position of a particle or an object in space with a vector function. And I said that vector function might be x vector of t, for instance. X is a function of t, but it's a vector, so it literally has an x component, a y component, possibly a z component. However, I said x makes people think along the x-axis, so some books actually still use that for the position vector, but most books, in my experience, use r for the position vector. So what I'd like you guys to think about is the position vector r vector, which I'm going to call r vector of t, and that's going to be equal to a constant r times the cosine. And I'm going to put some very specific symbols in here. It's the cosine of 2 pi over capital T times lowercase t times I hat. So you can put a square bracket around that if you'd like, just to make sure you realize all that stuff is the x component. And then we're going to say plus square bracket r sine, again, 2 pi over t times lowercase t, and then j hat. Okay, now this is a special vector. And in fact, what I'd like you to do is go ahead and see if you can fill out the following table. So what I'm going to do is I'm going to put a time here, T, and then I'm going to put a X here, and then I'm going to put a Y here. Okay. And the times that I want you to work out what X is and what Y is. So remember, X is whatever that thing R cosine 2 pi over T times T is, whatever that is for the given time, that's what you're going to put in X. And what you're going to put in Y is R sine 2 pi over T times T. So the first time I want you to work on is 0. And then I want you to work on capital T over 8. Capital T over 4, 3T over 8, T over 2, and then I want 5T over 8, and then 3T over 4, and then 7T over 8, and then just plain T. So for instance, I'm going to work out 0 here. The cosine of 0 is in fact 1, so I just get R. And the sine of 0 is 0, so I just get 0. Then T over 8, I'll notice T over 8, the T's cancel out top and bottom, and I get 2 pi over 8, which is pi over 4. Now, pi is 180, pi over 2 is 90, pi over 4 is 45. So this is basically the cosine of 45 degrees, which is root 2 over 2. So I'm going to say it's square root 2 r over 2. And the same thing happens with sine, because in this particular case, sine and cosine are the same at 45 degrees. So we're going to get square root 2 times r over 2. So T over 4 is going to get you, again, the top and bottom T's cancel out. I get 2 pi over 4. That's, of course, pi over 2. That means basically 90 degrees. The cosine of 90 degrees is, of course, 0. And the sine of 90 degrees is, of course, 1. So that's going to give you positive R. So let's let you go ahead and continue trying to fill that out. Feel free to use your calculator. I usually do this in my head, and that's fine, except for, as I get older, I tend to forget stuff. So I'm curious if I'm going to remember them all. But you guys can feel free to use your calculators. Put it in radian modes, because we are working this out as if it's in radians. So that'll help you. So you keep on working this, I'm working it, and hopefully we'll all agree on our answers in the end. Oops. If anybody knows why that keeps doing that, or can tell me how to fix it specifically, that'd be awesome. It just did it again. It aggravates the poo-poo out of me. This is going to be 0. This is going to be negative square root 2 r over 2 times negative square root 2 r over 2. Oh, sorry, that x was supposed to be a negative r. And then, dang it, there it goes again. Okay. Hopefully everybody got the same thing I did. Anybody get any different values than I got here? Okay. So no one's saying no, but let me put up my chat window just to make sure no one's typing no. All right. It looks like no one got anything different than I did. Hopefully you were all able to do it. The main thing that we notice here is this little point corresponds to t equals 0. And then this little point corresponds to chi equal, or excuse me, lowercase t. This one corresponds to t over 8. This one corresponds to t over 4, and so on and so forth. Okay. Now, what this suggests to me is notice that once you get around, for instance, to the bottom, this one is, this point right here is 3t over 4. And this one right here is 7. Oops. Ah, crap. There it goes again. This point is 7t over 8. And this point again just becomes t. So what we've discovered is the equation for circular motion, counterclockwise circular motion about the origin, and the radius of this circular motion is in fact the r that we see. Okay, so that's what that is. Now we can do something very instructive and helpful and stuff like that by remembering that remember the derivative of x with respect to t is what? Anybody?
Velocity?
Yes, that's velocity. And the derivative of y with respect to t would be the velocity as well, but that one's the velocity in the y direction, and the x one's the velocity in the x direction. So in general, the generalization of that expression is that the velocity v is dr dt, where r is our position vector. So what I'd like you all to do is go ahead and compute velocity as a function of time, which is gr as a function of time over dt. Now, it might help you to make the substitution that omega is the same thing as 2 pi over t, and that's also the same thing as 2 pi times f. And specifically, this t is called the period of motion. In other words, if you've got a cyclic process like this one, where you start at x equals 0, y equals, or excuse me, x equals r, y equals 0, and you return back to that after a time t, and then another time t, you're back there again, then that is a cyclic process, and the period of that cycle is t. Because that's the smallest amount of time you can spend to go from one place to the same place again. Additionally, this f up here is called the frequency. And that's usually measured in hertz or cycles per second. And I don't know why I wrote period. I don't know where that n came from at all. But that should be period. And that's usually measured in seconds. Okay. And this quantity right here, the omega, is called the angular frequency. And that's measured not in cycles per second, but in radians per second. So notice I wrote CPS there too. That's because I want you to remember that hertz is another phrase for cycles per second, even though my C is all of a sudden started looking like a letter from Turkish. So I had a professor who was from Turkey, and I remembered that some of his letters look like that. So I don't know that that's a normal thing or what, but that's what it looked like to me. All right. So if you keep that in there instead of 2 pi over t, it'll mean a lot less crap to write. So go ahead and try to work out that derivative. Remember, r is a constant. 2 pi and capital T are constants as well. So you're just thinking of those as numbers. This is, for instance, r of t could be thought of as 4 meters times cosine 6t I hat plus 4 meters times the sine of 6t j hat. You work it out. I'm going to work it out. And let's see if we get the same thing. So that's what I got for my first order derivative. Okay. Can anybody confirm that they got the same thing? In other words, just like we used r cosine omega t as x and r sine omega t as y, we then use that to find out what x is for a given time t, and we use that to find out what y was for a given time. So you could make a whole nother table now and figure out what the x component of this velocity is, namely the negative omega r sine omega t, and then you could make another column for the y, which would be omega r cosine omega t. The main thing that I wanted you to see with respect to that is that you would get a velocity vector that points vertically upward here. It points at a 45-degree angle there. It points perfectly horizontally here. Again, another sort of 45-degree angle, vertically downward, 45-degree angle to the right, 45-degree angle, and all these guys are velocity vectors. Okay. In fact, you might have realized that the actual r is an r who has, for instance, an x value of r at t equals 0 and a y value of 0 at t equals 0, in which case you'd see that this is r of t, and this is r of t, and this is r of t for each of those. Did anybody already figure that out, or did y'all feel like that might be what was coming, or does that surprise anyone? Anybody have any comments about it? So those red vectors are r of t's. The black vectors are actually velocities as a function of time. What I want to do now is ask you, do y'all think you could find the magnitude of the vector v of t? So all you have to do is remember this just has an x component and a y component. So you just have to use the Pythagorean theorem. and then make some simplifications, some really smart ones, and you'll find out something very interesting. So
Great.
what I recommend you do is first off, try to find the magnitude of R of t, and then try to find the magnitude of y, or excuse me, of v of t. So I'm going to give you some time to try to do that. Magnitude of R of t. And then I'm going to ask you to do the magnitude of v of t. Okay. So I'm going to work it out. You guys work it out. And remember what we're doing here. This should be very simple. There's no calculus here. If you weren't able to get the calculus to go from R of t to v of t, that's okay. I've now showed it to you. Now you need to make sure you understand how you're going to do it, because I'm getting ready to ask you to take another derivative of v of t. So you need to think about how we got from R of t to v of t using calculus. You need to make sure you can now figure that out and come up with the same answer we did. And then we're going to ask you to do it again, taking a derivative of v of t to get a vector called a of t, the acceleration as a function of time. So make sure you're doing that in addition to trying to find the magnitude of R of t. Now, the magnitude of R of t just means the square root of the sum of the squares of the two components. So hopefully I'll get you started. I'm going to start working on it. You'll see my work in real time. And once you've got enough, if you don't know how to do it right now, once you've seen enough, then jump ahead and see if you can beat me or start doing it on the V. So the magnitude of R, we can write it that way, or we can just write R of t. And what I'm going to get is the square root Okay. All right, now I've finished with the magnitude of R of t. I think y'all can all see exactly what trig identity I used. Anybody have any questions figuring out how I got the magnitude of R of t being R? Once you figured that out, then I want you to go ahead and compute the magnitude of V of t, which is right above that. So everybody sees the V of t is negative omega r sine omega t I hat plus omega r cosine omega t j hat. I'm going to take that magnitude as well. So the magnitude of V of t is going to equal the square root of. Notice when you square a negative quantity, the negative disappears. Hopefully y'all are well aware of that. People that finished calculus already should definitely, or at least finished one semester, should definitely know that. Okay. So anybody have any problems getting the magnitude of that V of t or the magnitude of the R? Everybody on the same page with me on that one? Okay, so what we're going to discover is I think where we get this is, I can't remember if it's like chapter 8 or chapter 9. We're going to get into rotational kinematics, where we're going to do the same sort of kinematics that we did in chapter 2, only this time it's going to be about things rotating about a center. And one of the first equations we're going to run into is V equals R omega, which is exactly what we just derived there. Okay. Notice the magnitude of the position vector R of t turned out to just be the radius of the circle. That's because it's going in a constant radius circle whose radius is R. So we see here that not only is this R of t describe a particle moving in a circle, but it's a particle moving in a circle at a constant speed, and that constant speed is the product of R and omega, which, remember, I said omega is the angular frequency measured in radians per second. You could also call it the angular speed measured like in degrees per second or revolutions per minute or something like that. Now I'm going to compute A of t. So A of t, the vector quantity, is the acceleration, and that's given by dv of t over dt. So we can now compute that A of t should be equal to, all I'm doing is taking the derivative of omega r sine omega t, but remember omega, t, and capital R are all constants. Okay, this isn't partial derivatives. This is just regular derivatives, but we're using symbols to represent, any range of numbers. So for instance, when I take the derivative of negative omega r sine omega t, I'm just going to say it's negative omega r, and now I got to take the derivative of sine omega t, which is going to be cosine omega t, but then I got to take the derivative of omega t, which is going to be omega. So I'm going to ultimately get negative omega squared r cosine omega t I hat. Now let's let you guys do the same thing for the y component and see if y'all can get the right answer for that one. So that one's omega r cosine omega t. So now I'm boxing off all the important things we've learned so far. All of these things should be things that you know. I would not say the R of t, V of t, and A of t is something that you necessarily want on an equation sheet, but I definitely suspect you should commit it to memory in case someone's were to ask you how to make up a vector function that is for a particle orbiting in a circular orbit of radius r. Okay. Is everybody able to verify that the acceleration as a function of time that I derived is the right one? Anybody find any mistakes in what I did? So one thing you want to notice with that is, and this is why I'm confident it's actually correct. One thing you want to notice with this is actually just equal to negative omega squared times r of t. So what that means is we see those r of t vectors that I drew in there. Each one of those, if you multiply it by omega squared and then flip the head on the other end, you will get the acceleration vector. So right here, the acceleration vector is this quantity. And this quantity. And this quantity. So that teaches us something. That teaches us that, in fact, in order for us to go in a circle, we do have to accelerate, and the acceleration is towards the center of the circle in the plane of the circle. So I think that's a very eye-opening sort of calculation and discovery. Now I'm just going to draw out the rest of these A of T's. Anybody have any questions on this? Again, they're all the same. Well, we'll see in a second once you calculate the magnitudes. Once you calculate the magnitude, you're going to see the magnitude of this acceleration is also a constant. So let's try that now. Everybody go ahead and calculate the magnitude of A of T. I'm going to do it. You can do it. Obviously, we're going to make use of yet another, or specifically the exact same trig identity to do this. And that's the key to making all of this make sense. The trig identity, of course, in case anybody hasn't yet figured it out, is sine squared plus cosine squared equals 1. And what we're going to do is factor out omega to the fourth r squared times parentheses cosine squared omega t plus sine squared omega t, which is just 1. So we end up getting the square root of omega to the fourth r squared, which is equal to r times omega squared. So that is, since I told you r and omega were actually constants, that means the acceleration magnitude is also a constant. So A is equal to r omega squared. And if you realize that omega from A equals r, or excuse me, from V equals r omega, omega is V over r. So I can also make this V squared over r. And those two are the expressions I'm trying to get with regards to the acceleration. So this is what we call centripetal acceleration. So what we've learned from doing this is that if we wish to go in a circle of some radius r at a constant speed, then your vector position function r of t is given by the one we showed you. Your vector velocity function is given by the one we showed you, and your vector acceleration function is given by the one we showed you. And specifically, the magnitude of the acceleration that you have to have has to be either r omega squared or v squared over r. Both are equal, actually. So it's, and we normally use v squared over r. And that has to be pointed towards the center of the circle in the same plane as the circle. That's the crux of what we discovered here. So we've got a lot of neat new expressions and kind of neat things, and we've used our calculus to discover some very interesting stuff. Anybody have any questions on that? All right, so I think that's a really good start on dealing with centripetal acceleration. You'll see there's very specific examples in the book, and we're going to work some of those. But first, I want to go into an example on friction. Specifically, now that we've learned about static friction and kinetic friction, the big thing we learned about static friction and kinetic friction is that the static coefficient of friction is normally bigger than the kinetic coefficient of friction. So if you imagine this, let's go ahead and stop sharing for a second. I'm going to do some more gesticulating, speaking with my hands. That's a fancy word for speaking with my hands. So I'm going to do some more gesticulating, not to be confused with masticating. Okay. And that's not what you think it is if you giggled. Okay. That means chewing. Masticating is chewing. Okay. So gesticulating is talking like this, and masticating is chewing. Okay. All right. So imagine this. Imagine this is a car riding down the road like this. The wheels actually rotate this way and this way on both sides. So as long as you're going straight, the tires are rotating in exactly the same direction that they need to, so that you're not wearing off the edges of the tires, right? If your tire was pointed this way and spinning this way while going that way, it would actually be skidding all along the edge. That's a problem. That does happen though. For instance, if you've ever driven in the snow and ice, sometimes you'll notice you'll get on a patch of ice and not necessarily know you're on ice, and you'll turn your steering wheel and hit the gas, and you'll just keep going straight even though the tire is like that. Because the tire is like that, it's not possible for it to rotate at exactly the any right rate, so that the tire is not in relative motion with the road. So in all times when your tire is rotating at an angle different than the car is moving by, then you are skidding. That is a kinetic friction issue. So you're in kinetic friction when your wheels are turned to any angle other than 0 from the direction you're going. Okay. Any angle other than 0 is with respect to the direction you're going. That's always going to count as kinetic friction, because you're clearly moving the road by with respect to the tire. Okay. Not only that, what you might not realize is when you're driving down the road, your tires are not in general slipping on the road at all. In fact, when you actually try to make them slip on the road by hitting the accelerator really fast, that's called speeding or spinning out. Okay. So you might be able to power brake it, which means you'd hold in the brake and then hit the accelerator real hard, keeping the brake in. And that hopefully with many cars, if they have a big enough horsepower and big enough torque in their engine, that would hold the car still while the rear wheels actually rotate. If you have a front wheel drive car, that might not work out so well for you. Okay. But rear wheel drive cars, you can do that. And that used to be something nerdy people would do to try to make them look cool, because they can put up a lot of smoke. It really ruins your tires though. So I wouldn't recommend doing it. But here's the other thing. When you're running down the road like this, the tire is rotating this way, so that basically the bottom of the tire gets to the bottom of its position at the exact instant that it's sitting still with respect to the road below it. A split second later, it's no longer at the bottom, and the road is now moving with respect to it, but the next chunk is coming down below it. So here's a neat thing. It turns out that when you're just driving along at 50 miles per hour, the friction that you have between your rotating tires and the road that's going by under you is static friction. That's a good thing, because remember, static friction is the larger of the two. So that means while driving, you're normally being held by static friction, which is a good thing. But as soon as you're driving like this on a straight road, everything's fine. But then all of a sudden you get to a curve. At that point, if you do curve and your tires turn just the right amount and your back wheels follow you just the right amount, then you're going to continue moving with static friction around that curve. But if instead, when you come around that curve, you do this and your back end, which a lot of vehicles have a lighter back end than they do in the front end, if that back end starts to slide out like that, what has happened is your rear wheels are now moving sort of this way while the road's going this way toward it. So you're in a kinetic friction situation with your rear tires no matter what, right? And in fact, if you did skid like this and you kept your wheels pointing straight forward or even slightly to the left, which was the direction you're going, now that you slid that way, you're actually turning pretty harshly to the left instead of barely to the left. So your front tires will now be in kinetic friction as well, and the car will tend to slide that way. So when you're going around a left turn, for instance, that's what I'm working out in my head, is a left turn. So straight ahead, left, right, when I go around a left turn, I expect that a slip might occur, and that would generally mean the back end would slip around to my right. Even I'm taking a left, but my back end slides around to the right. When a weatherman tells you to turn into the curve, what they mean by doing that is as your body or as your car tends to swing around like that to the right, you need to turn your wheel to the right as well because you're turning into, I said into the curve. I don't know why I said that, but you're turning your wheel into the skid. So you're skidding to the right. You want to turn your steering wheel to the right. And the reason why is you actually have a small probability as long as the car hasn't slipped too far, you have a small probability to take your tires that were nearly straight ahead and turn them so that they're now straight ahead, even though the car is not going straight ahead. So they're actually parallel to the direction the car is going. That's what you're shooting for. If you do that, then automatically static friction kicks in with your front tires. Your back tires don't have any help. They're going to continue to slide, but if you have enough friction in your front tires, which is normally where the largest normal force is because the engine's in the front, then you're going to be fine. So that's the big trick of turning into the skid. Now I'm going to open up my iPad again and give you a little drawing to help you make some sense of that in case you didn't understand it. Does anybody have any questions on that? Thanks, Al. Andrew, that's it. I thought I called you Alex. Sorry about that. I knew it was an A word. All right, so uh static friction slash kinetic friction. So let's imagine you lift a car up on jacks. Okay. Let's say you lift a car up on jacks, which I'm just going to picture like there's a big piston with a jack on it, which obviously is not the way jacks work, but we're going to deal with it. Okay. And now you hit the accelerator. Why? Now, this is not a safe thing to do. I'm not recommending doing this, but you strap yourself to the jack stand and all that good stuff and make sure your tires aren't going to touch anything and make sure no kids or animals or dogs or cats and puppies and pygmies and pigs and all sorts of stuff like that. You're going to make sure all those are away so nothing could happen. But what you're going to imagine doing is hitting the accelerator and driving it, basically pretending to drive it with your foot on the gas until the speedometer reaches, let's say, 30 miles per hour. Okay. That's a lot of speed. This is not something I recommend doing in reality. But you can try it at like 2 miles per hour as long as you make all the safety precautions. And that would give you a little estimate. Uh, and then I need you, while you're thinking about doing that, I want you to answer some questions. Okay. Here's a picture of, oh, that's really bad. I forgot I have the ability to draw circles on here that are nice and neat. Okay, so here's a picture of any one of the tires. Now we're going to imagine this is a four-wheel drive vehicle, like a real posi track four-wheel drive where all four wheels are tied, just so we could say this is any of the four tires and therefore every of the four tires. Okay. Now, when a car is traveling at 60 miles per hour, how fast do you think the axle is going with respect to the earth? And I'll say 30 miles per hour since I decided to do 30 miles per hour. Okay, so imagine for a second we're actually driving down the road instead of on a jack. All right, and we've got the speed set at 30 miles per hour. How fast do you think the speed of the axle, or how big is the speed of the axle with respect to the Earth? Anyone? So I'm going to call this the velocity of the axle with respect to Earth. So that's VAE. And we're going to assume it's going in the positive direction. So I'm going to call the answer positive. Would you all agree that the axle should be moving at 30 miles per hour if the car is moving at 30 miles per hour?
Yes.
Okay. So we're going to say positive 30 mph. Okay. Now, when speedometer reads 30 mph, and the car is on, whoa, no, is on the lift, how fast is the bottom moving? Okay, so we're looking at the car from the right here. The car's in forward. This could be the front tire or the rear right tire. Either one doesn't matter. We're actually imagining the car as if this is forward. I noticed my tail made it look like it could possibly be going the other way, so I just want to make sure. So does anybody have any idea about how fast this point right here is moving and in which direction? So one thing you can think about is imagine instead of it being on a lift, let's say it's on a hanging from a helicopter in a perfectly level situation, and the helicopter is flying perfectly parallel to a long, straight, level road at 30 miles per hour. Okay. So you're in the car, you've got the speedometer set on 30 miles per hour, and you're holding your gas pedal down to maintain it at 30 miles per hour. And the helicopter is flying at exactly 30 miles per hour over the road, going the same direction that the car would be going. So if you were to drop the car instantly, would there be any initial skidding with that bottom section of the tire?
No,
No, that's right, because the tire is moving at exactly the right speed and at the exactly the right direction. Because if you're flying in the car and it's going, say, due north, the road is going by you due south at exactly that speed. So it turns out the velocity of the bottom of the tire, which I'll say velocity, actually I'll do it in red. I'll say the velocity of the bottom of the tire with respect to the car is actually going to be negative 30 miles per hour. And what about the velocity of the top of the tire with respect to the car? Can anybody tell me what that is?
Also 30?
Yes, also 30, but that one would be positive, right? So the velocity of the top of the tire with respect to the car is equal to positive 30 miles per hour. That's kind of a weird thing, but if you've ever driven a tractor or looked at and paid attention to a bike, you see that in fact the bike wheel is in fact moving the opposite direction you are, uh, in some sense, as the bottom of the tire. So for instance, when you're riding your bike forward, the bottom of the bike tire is going backwards at exactly the right speed, and the top of the tire is going the same speed, but it's going ahead of you, in the same direction you're going. So that's the way that works. Does that make sense to everyone? All right. Now that we know that, we're going to imagine a scenario of a car moving at 30 miles per hour. So if the velocity of the car, I think the car would be fine. Yeah, I'll say if the velocity of the car with respect to the earth is positive 30 miles per hour, and the velocity of the axle with respect to the earth is 30 miles per hour. What's the velocity of the axle with respect to the road is one thing we could answer. But the bigger thing I'm trying to figure out is what is the velocity of the... Nah, I don't think I want to do it this way. I'm actually trying to make it a little worse for you. What I'm trying to get at here is the velocity of the tire, the bottom of the tire with respect to the car is going to be, in fact, exactly the negative of the speed that the car is going. So if the car is going 30 miles per hour, the bottom of the tire is going negative 30. And the road is going by at negative 30, so that the velocity of the tire with respect to the road at the bottom of the tire is zero. That's the main thing I'm trying to point out here. I was going to use my relative velocity formulas to work that out, and that's what I've done in the past, but I'm not feeling it right now. I've asked a few questions, and it didn't look like people answered. I did have my chat off again, though, so that could have been part of it. Yep, looked like somebody answered. Sorry about that. Oh, no, that was somebody putting their name in. Anyways, that's the main thing I was trying to show you, is that when your car is, say, going 30 miles per hour, then your tire is actually rotating at 30 miles per hour. What that means is the velocity of the top of the tire with respect to the road is actually going to be 60 miles per hour, because it's twice as fast as the tire is really going and as the car is going. The bottom of the tire is going to be going negative 30 miles per hour, and the axle itself is going to go positive 30. So the whole reason I did all that is that you'd see that the velocity of the road with respect to the car and the velocity of the bottom of the tire with respect to the car are equal. So I'll just write that out here. When traveling north at 30 miles per hour, the velocity of the car with respect to the earth is equal to positive 30 miles per hour, and the velocity of the earth with respect to the car is negative 30 miles per hour. Of course, you already knew that because that was one of the rules when I gave you the addition of velocities formula that says VAC is equal to VAB plus VBC. Long as the middle two match each other and the outer two match the left-hand side one, then the formula is valid. But I said that came with the additional rule that VIJ is equal to the negative of VJI. So I just made use of that. I didn't intend to, but I did make use of that. And I'll write that over here just to remind you. The velocity of A as seen by C is equal to the velocity of A as seen by any letter, really, long as it matches the first subscript on the second variable. So that's our addition of velocities, or our relative velocity formula. And then it has that other rule that Vij is equal to negative Vji, which also looks like Newton's third law, which I told you F12 is equal to negative F21. That's Newton's third law. So I'm just bringing that up to remind you that it looks just like Newton's third law, so maybe that's twice the chance for you to remember that that equation. Okay. So when traveling north at 30 miles per hour, we call the velocity of the car with respect to the earth positive 30. I'm just saying, hey, I'm considering north the positive direction. The velocity of the earth with respect to the car is, according to the driver, the road is going by him in the opposite direction at 30 miles per hour. That's why we got negative 30. Okay. But, oops, I should have kept that in green, kept that in blue. However, the velocity of the bottom of the tire with respect to the car is equal to negative 30 mph, and therefore the velocity of the bottom of the tire with respect to the earth is equal to 0. That implies static friction. So that's it. And I mean, that should be somewhat obvious, but it's surprising how many people don't get that. Specifically, if you had the ability to allow a car to ride over you, let's say at a decent speed, but you're going to have a camera that can take really good pictures at any speed. Let's imagine that. So if you imagine a really thick plexiglass see-through floor that actually can hold up a car, you're going to imagine this car going over top of you, and you're going to take pictures as the car rides by. What you're going to figure out is that there is no sliding going on between the part of the tire touching the plexiglass and the plexiglass surface itself. Now, as soon as that part of the tire goes behind the part where it's touching, then yeah, they're going at entirely different velocities. There would be skidding in that case, but at the instant it's at the bottom, the velocity of the tire bottom exactly matches the velocity it has to have to make it no relative motion relative to the road below. So that's why you have static friction. So that's the big part of making sense of this. Now we can imagine going around a curve. So let's imagine I talked to you about taking a turn to the left. So we're going to imagine this is a road turning to the left. Initially, what is going on is you have a car. Oops. You have a car like this. Oh, okay. And then you have the tires, and they're pointing parallel to the path of the car. The car is moving this way. So that's our velocity. And I'll just say tires aligned parallel to the direction of travel. And that's at this part right here. Now we're going to continue on and get to this part of the curve, say. Get to this part of the curve, say, and I'm going to imagine that the car starts to skid. So what has happened is the car was in that dotted position, but because of the iciness of the road, the back side has begun to spin around the front tires. Notice the back tires generally don't turn. There are some vehicles that allow the back tires to turn, but this is not the case with that. And in fact, the instant it happens, you're probably not yet realizing it's going on, so you haven't adjusted your tires yet either. Those front tires might actually be turned just slightly to the left because they were trying to go to the left, but the main thing is they definitely do not align with the direction you're going, because now what's happened is the direction you're going is this way. And the tires are pointing this way. So here, tires not parallel to direction of travel. So you must turn into the skid. Okay, so what that means is, let's look at your steering wheel. Whoa. Looking at your steering wheel, are some SpongeBob SquarePants. Okay, looking at your steering wheel, that means you're supposed to turn it to the right. And you can sort of see that as this. What I'm going to do ideally is I'm going to choose another color. I think I'll use purple. What ideally would like to do is turn my wheels so that they're now parallel to the direction of travel. So I'm going to say, as seen in purple. Okay, so does everybody now get what I mean by turning into the skid? And it is completely consistent. It's exactly the same advice for all the wrong reasons, but it's exactly the same advice that the old car gave the new younger car in the movie Cars. He said, you got to turn left to go right. And they're like, all right, crazy man, whatever, blah, blah, blah. Entirely different scenario, a horrible way of instructing him, but still an entertaining movie that I enjoyed. Okay. But the main thing is he's right. And you saw as the car went around the curve, for instance, to the left, the back end slid out to the right, and he turned his steering wheel to the right. And that was able to allow him to keep on the path, even though he was spinning out all the way around the curve. Now, in this case, if you're actually doing this on an icy road, if that car the back end slips out so far that your steering wheel is not capable of turning the wheel far enough, then you've already lost at that point. There's not, I mean, you still want to try in case you're wrong about the relative motion and stuff, but there is a point at which you lost. So you don't want to be distracted, not paying attention, or have slow reflexes for whatever, hopefully legal reason you might have slow reflexes on that day. The main thing is you want to immediately start turning. As soon as you feel the back end of your vehicle go off to the right, you want to start turning right. As soon as you feel the back end of your vehicle going off to the left, you want to turn the top towards the left. And you want to do it not spastically. You want to do it, smoothly in an attempt to try to just match the angle that you're going. Now, once that happens, kinetic friction will immediately turn itself back into static friction, and it can only pretty much do it with the front tires because only the front tires are now parallel to that velocity vector you see. See how the purple tires are now parallel to the blue vector, whereas before they were parallel to the little red arrows. The blue vector is the direction you're going because you went into a skid, right? So anyways, hopefully that helps. The time is actually up. It's now 6:40. I've covered the main basics, so you can actually start working problems. You know all you need to know. You just need to practice. So you can start working all the problems in chapter 5. If you want some examples, obviously the ones in the books are actually very good. But there's numerous ones where I just talk about centripetal force, centripetal acceleration. So do searches for those on my YouTube channels: centripetal force, centripetal acceleration, just the word centripetal. Do searches for friction, on my YouTube channel, and you should find a ton of examples in addition to the ones in your book. And of course, next time when we meet, I will be going over some of that some more. Don't forget your online test. Your second online test is due by the 4th. I believe that is Friday, so make sure you get that done. The practice test should stay available for that whole period so that you can still take it in preparing. And then next week, we will have a face-to-face, quote unquote, proctored test where you're either going to have to set up some time at the testing center on the campus closest to you or whichever campus you want to go to and set up a date and time sometime between Monday of next week and Sunday of next week. Well, I should say, yeah, Sunday, the end of next, or not this coming Sunday, but the following Sunday. Okay. So make sure you can book it there. Make sure you find out what you have to do to go to a testing center. I'm going to make a test that you can take with the Respondus Lockdown browser on and with the Respondus monitor on, and I'm going to make it available for the testing center where they can turn off the Respondus monitor. If something else happens, then I might have to force someone to take it with me watching them through this Respondus monitor. But hopefully that's not going to be the case. So make sure y'all get that done. You guys are free to go. Make sure you already chatted your first and last name in the chat box if you haven't already. And thanks for coming, everybody. I'll wait for the last person to leave if anybody has any questions.
I did have a couple questions on some of the practice stuff.
Okay, go for it, Dylan. You want to share your screen with me?
Well, I had sent you a picture earlier earlier today of one of the questions.
Okay. Yeah, the one with the vector, that was you?
Yeah.
Okay, yeah, I actually looked at that. I guess you got a different legal name than the name I keep seeing. That's why.
Yeah, sometimes it shows my first name, Jasper.
Yeah, that's what it was, Jasper. Yeah, okay, that's cool. So yeah, this was the one that had 6 meter or 6 is the magnitude at 30 degrees north of east, and the other one was 4, I think, meters, and that one was at 30 degrees west of south. Is that correct?
Yeah, correct.
Okay, so let me show you exactly how to work such a problem. Whoa, Nelly. I just opened up the wrong one, I think. Okay, yeah. So what we have is vector A is equal to 6.0 meters at 30 degrees north of east. I put them in capitals to make sure they stand out. And B is equal to, no, it's 4 and 6, wasn't it? Not 6 and 8.
6 and 4.
Oh, 6 and 4. Okay. All right, and I'm looking for. Okay. The other one was 4.0 then, or was the first one 4? I can't remember now.
A is 6, B is 4.
Okay, gotcha. Yeah, I finally found the email. I mean, the text message you sent me. I was trying to look for it, but it moved down because I'd opened it. And north of east, and B is 4 meters, 30 degrees west of south. So this is at 30 degrees west of south. And they want to know A plus B is question mark. So what I'm first going to do is I'm going to draw a coordinate system so that y'all have an understanding of what these directions mean, just in case there's some ambiguity as to how that works. That's always an underlying problem, or I should say that a lot of times that's an underlying problem. What we're also going to say is Y is the north direction, X is the east direction, negative X is the south direction, and negative Y is the west direction. So when I say 30 degrees north of east, what we mean by that is I'm going to try to make this about 30 degrees. And that's 30 degrees north of east because I went to the north side of due east, and that's my vector A. Okay. Now, what I want to do is a second vector that is at 30 degrees west of north. So I'm going to imagine another coordinate system right here. I'm going to draw it perfectly horizontal there, perfectly vertical there. Now I'm going to, whoa. Okay, I'm going to leave that alone. And this is going to be shut down like that. Okay, so now what I need to do is go at an angle of 30 degrees west of south. So south is straight down. What I'm going to do is attempt to go 30 degrees like this. So that is what we mean by 30 degrees west of south. Okay. Now, this blue vector is vector A. I didn't write down A yet because I wanted to make sure I left room for the symbol with the other vector. So that's what the two vectors are like. We can see, for instance, that the sum, since I've written them head to tail, the sum vector should be roughly like this. So I know it's at least in the fourth quadrant. I suspect it's going to be, I didn't take into account the sizes of these. It looks, in fact, like the red one, which was supposed to be 4 meters, is actually a little bit longer than the blue one. But anyways, that's the actual picture. So what I'm going to do is first find the x component of the a vector. And we can see that would be given by a times cosine 30 degrees, and it's a positive component. So I'm going to say positive 6.0 meters times cosine 30 degrees. And when I do that math, I'm going to get,
It's 5.2.
thank you, 5.2. That's going to be positive 5.2. I'm going to double check with mine just in case we had a problem with units or something like that. And yeah, I got 5.19. So that's good enough. Actually, I want to call it 5.196 just to keep a couple extra sig figs, because sometimes that can be part of the problem with working with homework systems as well as Canvas. So I'm going to call this 5.196 meters positive. A sub y, by the way, let me show you. I'm going to use green for a positive vector. So the x component of that vector is that guy right there, and the y component is that guy right there. So that's a sub y, and this is a sub x. That's how I knew they were sine and cosine and that sort of thing. So a sub y is clearly positive again. So I'm going to say it's positive 6.0 meters times, this time I'm going to say the sine of 30 degrees, which I think you guys know is supposed to be a half.
Yeah, so I got 3.
So this should be 3.0 meters. Okay, and positive. Now I'm going to do the same thing with B. So B sub x is going to be, in this case, we can see the B sub x is going to be negative. So I'm going to write negative 4.0 meters. And now in this case, the x component is in fact given by the sine. So now I'm going to do sine of 30 degrees. And of course, that gives you negative. Is that what happened?
I didn't. I did it as cosine still.
Yeah, that's one of the big things is people always think cosine's x and sine is y, but when you start measuring it off like a y-axis or something like that, it's a very different thing. So yeah, that's exactly the likely culprit. Now I can do b sub y. Now b sub y is a negative component as well. So I'm going to put negative 4.0 meters times, this time it's cosine of 30 degrees, and 4 times cosine 30 is equal to 2 times the square root of 3, which is 3.464.
Yeah, I got negative 3.5 and 2, but I got them switched. I got it x and y switched, obviously, because I did cosine for one and sine for the other.
There you go. That would do it. So now all we have to do is add the x component. So I'm going to say 5.196 minus 2 is clearly equal to 3.196 meters. And this is r sub x, where I'm calling a plus b is the resultant vector. That's why I used R. And then R sub y is going to be 3 plus negative 3.464. So this is going to be negative 0.464 meters. So if we wanted to go ahead and express that as a vector in magnitude and direction notation, which is what the problem did, then we should go ahead and plot them. I can see that the x is positive, but the y is negative. So that should really be in the fourth quadrant. So I'm going to draw it where only thing I care about is this x and this is y. And what I'm going to do is I'm going to draw the x component to be nearly 4 units in the positive direction. Actually, I should keep it closer to 3, to be honest with you. It's just barely over 3. So I'll say just barely over 3 is like that. That's 3.196 meters. And by the way, technically, we only have 2 sig figs. So these guys are actually only good to 10th place. Now the other one is just under a half and it's negative. So I'm going to take this guy and draw it like this. And that is 0.464 meters. And the resultant vector R is that little guy. And its magnitude would be 0.464 meters squared plus 3.196 meters squared, which is going to be really, really close to 3.196. Squared. Take the square root of that. That gives me 3.229. So that should be a roughly 3.29 or 3.2 meter magnitude. And the direction should be, I'm going to call this little angle in here.
Tangent y over x.
Yes.
Yeah.
I'm going to call it phi. And phi should be the inverse tangent of, notice I'm not putting any of the signs in there again. 464 meters over 3.196. That should be a very small angle. So I'm going to say shift tangent inverse 0.464 divided by 3.196. I've actually discovered my calculator sometimes does something weird unless I put that in parentheses. So I'm going to check that. I did tangent inverse parentheses 0.464 divided by 3.196. That gives me 8.26 degrees. So I would say this vector R is about 3.2 meters at negative 8.2 or negative 8.3 degrees.
Yeah.
That's one way of expressing it. They might say 8.3 degrees south of east. That would be acceptable as well.
Yeah.
So that help you?
Yeah, I saw where I went wrong.
Yeah, good deal.
I also think there's one question that's messed up.
Okay.
Because it asks this question in a different way. So the question is like a child throws a ball at initial speed 8 miles per second at an angle of 40 a meter above the ground. How long is it in the air?
Gotcha.
There's 2 versions of this exact question.
Yeah,
Throughout
one gives you the final velocity or asks you for the final velocity.
one gives you it's time and I think range, or maybe either way, it gives you your choices are still the same for both questions.
Gotcha.
So I think that's what's wrong. It's the same numbers because when I've done the time one, I've done it before and got it right. And then on this one, you do it again and it's the exact same numbers, but the option isn't there.
Okay. So I did work one version of that problem the other night. So if you looked at my actual video on, oops, if you actually looked at my video for 242 class, which obviously you have no reason to because it's 242, that's not what you're about at all. You would see at the end of that, I had a student from 241 come and they asked me that very question. They said a velocity of 8 meters at 40, or excuse me, 8 meters per second at 40 degrees above the horizontal. The ball is launched at 1 meter high, and it asked what the final velocity is. Basically just before it hit the ground. What I found for the time period was 1.217 seconds. So that's what I wanted to get for you, just in case, since you said they were asking for the time. That's what I got, and when I used that time, I got exactly the same answer I got for the final velocity, doing it an entirely different way. So I'm confident that the answer is about 1.217 seconds is how long it takes the ball to get to the ground. There's another one that's a negative amount of time, and that's basically imagining if the thing was fired from ground level, how long ago would it had to have been fired at ground level to reach 1 meter above the ground right now and moving at 8 meters per second at 40 degrees. So that's literally what that negative time is. Does that help you? I will check the question to see if it does have if it has the wrong answer choices, because obviously that's not a usable problem, but I will check that. There we go.
Okay, yeah.
Okay. Sorry about the dogs there. Yeah, do you see the solution too? So
Yeah,
you can also look.
I had done it the same way you did it, but
Okay.
I was I had done it once on the first time I got it right, but then it asked it a different way, and the choices were different.
Right.
So that was what was weird because it's the exact same numbers, but it didn't
Yeah,
have the same.
as soon as you said 8 meters per second, 40 degrees, I knew it was the same problem. And I knew that hers happened to be about what the final velocity was. So, it might have been asking you an entirely different question, or it might have been a screw up where they put the wrong answer choices. But I will check the bank and see if there's wrong answer choices on one of them. It's easy to find. I know exactly where it is. And if it is, I'll pull that out or correct it.
Um, go back to chapter 4 real quick to get to those.
It's kind of confusing looking at the solution, but what I told her to do was, notice I wrote that the equation A equals dV/dt, where A is a constant. That's the first thing I wrote under the diagram. And if we were to integrate that, we'd get V equals AT plus some integration constant. And then when we said the velocity at t equals 0 is V0, it would become that equation V equals V0 plus AT. Then using V equals dx dt and putting on the other side of an equal sign V0 plus AT, if I integrated that, I'd get 1/2 AT squared plus V0t plus an integration constant. But if I assume that the x position was x0 at t equals 0, then I'd get that equation x equals 1/2 AT squared plus V0x times t plus x0. So I did that to show her that anytime a object has a constant acceleration of a, that equation is valid for its position as a function of time.
Mhm.
In the case of horizontal motion, that is a constant acceleration, but it's a very special constant acceleration in that when we study projectile motion, we ignore air resistance. So there's no acceleration. The acceleration is 0. So the x equation would turn out to be just V0x times t, and maybe plus an x0. The y equation, though, is going to turn out to be what I wrote down here, which is this y of t equals negative 4.90 t squared plus 5.1423 t. That's, by the way, 8 times the cosine of 40. And then 1 meter was the initial height. This is the equation you get for the x component, because we took the initial x position to be 0, and the 8 meters per second times the sine of 40 gives me 6.1284.
Yeah, I got the same numbers you did.
That's cool. Do you see the red stuff right here?
Uh-huh.
So I wanted to show her that she didn't necessarily have to do it that way, even though that's what I suggested all my students do. She could still use her kinematic equation. So in that case, I just told her to use this one, and we worked it out. And of course, I had to make sure I chose the right direction. So the right direction was negative, and I got 6.785. Now that's just the y component. The x component, of course, is going to stay 6.1284. So that's why I had that there and that there. But you can see later on when I take this time and I plug it back in this equation, then I do get the same velocity.
Yeah, so I had started by getting the X and Y component, and then I found the flight time. And then once I found the flight time, I used the time to find the final
Velocity.
velocity.
Did you remember to combine the final velocity with the final x velocity?
Yeah, and get the magnitude.
Yeah.
Yeah.
Good deal. Okay. So it sounds like you did everything right. Yeah, I'll look for it having a erroneous problem, and hopefully I can fix it. The way I worked it is I should have one bank and all of them are copies of that. But hopefully that's the case.
So in chapter 4 on this one, the first question is an object is moving with constant velocity in a straight line. Which of the following statements is true?
Okay.
So if it's constant velocity in a straight line, I put there are no forces acting on it because it's constant. It wasn't it as if no forces are acting on it, it's going to stay in whatever state it's in.
That's a possibility, yes.
Okay, so
What
I put
other
that,
choice?
and that was incorrect.
Okay, so the other choices might have been the
More
sum of
correct.
the forces is zero, or the net force acting on it is zero, something like that.
Oh, the net force on the object is zero,
Yes.
but isn't it the same thing as saying there are no forces
No
acting on
forces.
it?
Sorta, yeah, but the reason why they parse it this way for you is we sometimes say, hey, I know that a force of 9.8 newtons is acting on a 1 kilogram object in a gravitational field while the 1 kilogram object sits on a tabletop. It's sitting on a tabletop perfectly still. Is this the only force acting on it?
Okay, because the net or all the forces cancel out, making the net force zero, but there still are forces there.
Exactly.
Okay.
So you can use it sometimes to detect that there has to be at least two forces, because if you got one force, you can't have zero unless the other force cancels it out. So it's almost impossible to have one force essentially acting on an object and it have a constant acceleration or a zero acceleration, excuse me.
I think that was all for those. Yeah, I think that was all the questions I had for right now. But I was going to ask you about like some of the stuff you were just going over for chapter 5.
Uh-huh.
So
Hopefully that helped you a little bit.
yeah, that did. I was going back over some of the stuff that I had from the other physics class I took.
Uh-huh.
Um, and I guess for the angular stuff, we basically had kinematic equations that were just angular.
Right.
Is that what you're talking about, like later on in chapter 8?
Yeah, we're going to do that much later. But what I've seen over the years and what I felt when I took this class myself is I was really bothered by the derivations of the centripetal acceleration being v squared over r. They were kind of hard to follow and stuff like that. And then I figured out this way on my own while I was still a student, and then it made sense and I was able to get past it. I'm a weird learner in that I don't like being told, you know, just accept this and run on. So it caused me a little bit of headache. So I've tried to introduce it this way for people like me, and because it's, you know, one of the few times where I can actually get the students to what I think is fairly easily derive an expression that we use in the class. So we're not going to do those kinematic equations for a while, but we are going to use centripetal acceleration now.
Okay, and I see, yeah, I see ours similar as the AC V equals V squared over R, or
Yeah.
AC equals W or omega squared R.
Exactly. Yeah, it's getting there. Like I said, I didn't want to dip it too much, but in this chapter, they're also going to mention that they have a centripetal acceleration as well as a tangential acceleration. So they're getting even closer than we are now to the kinematics of rotational motion.
Okay, yeah. And we had the distance, they used S equals R theta.
Yep, that's the trigonometry definition of radians, for instance.
Oh, okay. Okay, so yeah, some of the stuff they used were just slightly different. I was like, some of this looks familiar, but it also looks a little different at the same time.
Right.
For acceleration, they used A equals R, and then the Greek A
Alpha.
alpha.
Yeah. Yeah, that comes from S equals R times theta. If you take the derivative of it with respect to time, you get ds dt, which is velocity, and you get d theta dt, which is omega. So v equals r omega. Then you take the derivative of v, you get a, and then you take the derivative of omega and you get alpha. So that's where the a equals r times alpha comes from.
That is super confusing.
Yeah, it doesn't have to be that bad, but yeah,
Many different alphabets.
it's basically, yeah, S equals R times theta. And then ds over dt is equal to R, because R is going to be a constant. This becomes V equals R omega. And then dv dt equals R d omega dt. That becomes A is equal to R times alpha. So yeah, that's what we're actually doing. And
So,
you're pretty close to it already with what we did.
so when you showed earlier that the omega also meant something else, I can't remember what you wrote for it.
2 pi over t.
Okay, what does alpha stand for? Something like that as well?
Yeah, in some sense. So omega was 2 pi over the period, which you can also write as 2 pi times the frequency. And V is equal to R omega, says that V is equal to R times 2 pi F. So you can see that once you take the derivative of all this, the quantity that comes in here is going to be alpha. So if I say dv dt is equal to R times d by dt of 2 pi F, then this weird thing pops up. We get A is equal to R times 2 pi df over dt. This quantity is alpha. Whoa, no, they don't know. Oh, I see. This quantity right here is actually alpha, but we normally think of it in terms of omega instead of F. That's why it doesn't pop out when we did it,
Okay.
because omega is our d omega dt is alpha.
Okay, I got you. Cool.
Because alpha, for instance, would have units of, instead of meters per second, it would have units of like radians per second per second.
Okay, yeah, and I remember when we did when we were doing the uniform circular motion is what this was under. Uh, a big thing was that we had to use radians and stuff like that because none of the formulas would work with revolutions or something like that.
Yeah, it's weird. A lot more work than you think they will. So we always, as teachers, we say, just use everything in radians, and it'll make it easier on you until you are so confident that you can use it without radians. And then basically on our own, we figured out when we could do it. But yeah, that's basically it. You can surprisingly use degrees a lot, but anything that basically used S equals R times theta has to have theta in radians usually. So, but yeah, the good news is, like I said, it's not quite as bad as you always have to convert to radians. But if you always do convert to radians, you will always get the right answer at least.
Okay. All right, that should be all I was wondering about.
That's cool. Well, I hope that helped, Dylan. Feel free to keep sending me texts and stuff if you need them, like you did today. I was actually out when I got it, and I was going to look at it when I got here, but I didn't get here until just before class, so I didn't get enough time. But at least we got to cover it after class.
Yeah, that's why I wasn't worried about it. I figured if you didn't get to it during the day, I'd be able to ask you this evening. I had some
Yeah,
time at work to get some work done today, so
I thought I was going to have time doing it when I was coming home, but I tried to use the polar function on my calculator, and I forgot how to use polar function on my calculator. So I'd have to actually do the work to figure out what the right answer is. That's why I stopped.
yeah. When I first got my TI-84 plus or whatever it is, I made a Word document on my computer that's labeled notes because I can never remember how to do certain things if I didn't use it for a while. So
Exactly. That's the way I was with my HP. I had a manual that was like this thick, and then I had this little help guide, and I had like 6 things in there that I always use. So I just carried that around with me.
yeah, it's great because they can do way too much, and I don't use it enough to remember how to do it.
Yeah, exactly. Well, you have a good one, Dylan. And again, don't forget to do your online test and be prepared for next week's face-to-face / proctor test.
Yeah, I sent an email today because you have to schedule it in advance. I sent an email today trying to take it Monday. Usually they're pretty quick in replying to at least say like we got it or something, but
Right.
I never heard anything because I sent it to them at 10:30 this morning. I never heard anything back from them, which was
They might be waiting for me to initiate mine. I'm going to probably do mine either tonight or tomorrow morning, and then you can expect to get a response from them. Sometimes they literally just want to wait until the instructor calls it in, but normally they normally do, like you said, do it within minutes of getting it.
yeah, and that's what I was wondering too. Is I know sometimes if you send it in way too in advance, they won't. If the teacher hasn't said anything, they won't do anything.
Right.
But you said it was gonna be like a respondus thing. Are they gonna have?
Yeah, they have all the software they need and all that
Well, I
stuff.
mean
What I'm probably go ahead.
formula sheet.
Yeah, what I'm going to do is I'm going to send them a PDF of the formula sheet and they can print it out there. And that way you don't have to bring anything because otherwise they're going to have to take a picture of it and send it to me just so I can verify that nothing was written on it that wasn't supposed to be and all that stuff. So it might just be easier. And not only that, this weekend I'll send y'all an email. I'm going to actually give you a version. Well, actually, you already have it. My 202 class doesn't have it, but the formula sheet that's listed on our Canvas page that you have access to, that's going to be what's going to be a copy of. The actual constants will be down at the bottom. Is that acceptable, or do you think y'all really need the constants up front too?
I'm honestly not sure. I always write my own formula sheets because I always struggle with the algebra of rearranging it.
Yeah.
So I always write out like each formula and then how to solve for each letter in that
I
formula.
gotcha.
Because if I try and do it during the test, I'll end up screwing something up or I'll spend too much time trying to rearrange the formula.
Yeah. Well,
So
that,
I've
that
always,
practice of making one and especially solving for the various variables, that's excellent to do, even if I provide a formula sheet for you. So keep doing that. That's a good skill for you as long as you have time. If you
well,
don't
yeah,
have time, then you just want to make it because just making it's probably going to be enough to help you with it to some extent.
well, yeah, I do it on my own so I can look back to it. But then when I go to take the test and realize I don't have my own formula sheet, that's where it becomes an issue. And I'm like, oh crap, I've been relied too long on my, like babying myself with my own formula sheet that I wasn't ready to not have mine.
Right.
I've been trying to practice with just using the one provided through you.
Yeah. Well, that's
Okay.
cool. Well, have a good one, Dylan. And like I
Too.
said, if you hear anything or if you need anything, I'll be here.
All right. Thank you very much.
You're welcome. Good
Have a good
evening.
night.
You too. Bye-bye.